So let's say you want to be famous on YouTube, right?
Yeah.
The way that videos go viral, if you log how many views they get, is they start off with a couple views, and then people start sharing and sharing and sharing, and very quickly a lot of people have access to your stuff, and you've gone viral. This follows an exponential trend, because is this a straight line?
No.
What's it called now? It's a curve. We're using curves now.
Positive.
Okay? This one's increasing. Or let's say like last time on the breakout, or if you want to become a doctor, you want to cure diseases. You have to understand how viruses spread, and viruses spread by starting with one person and very quickly infect a lot of people. This is called exponential growth, okay? They're modeled by exponential functions. So we're modeling things by these functions that happen in real life. I'm going to be giving you math examples for today mostly, but we will get to the real world examples eventually. Deal?
Yeah.
All right. Now, this is a different formula than we've ever used before. If you have a highlighter, I want you to highlight the formula here on the top of your page. It's f of x equal to a times b to the x power. F of x, circling it is fine. F of x equal to a times b to the x. Now, here's the thing. This is not on your formula chart, which means it's something you have to memorize. But it's real easy because it's two letters.
F and A, B. Well, there's three.
Well, f of x is just a fancy way of saying
A, B, F times X.
oh my gosh, it's not f times x. What is f of x a fancy thing for?
F to the X power.
I'm gonna cry.
Right? No, it's not. My bad.
Wow.
Oh, all right. We haven't used that in a while.
We haven't. Don't ever forget it. F of x is the fancy version of y because it's a function, okay? So yes, x and y are in there, but you have two letters that you might be using. You have an a and you have a b, okay? What do you notice about the x, though, about the variable? It's an exponent. Guess why they're called exponential functions?
Because they have exponents.
Because its exponent is the variable. So we're going to make that note for ourselves. The reason that this is an exponential function is because the variable is an exponent. Sorry, I had to write bigger than the box. The variable is an exponent. If I'm asking you to write an exponential function and an answer choice has a variable that is not an exponent, should you pick that one?
No.
Cool. All right. Good. Good talk. Now, the only two letters you have left to describe are A and B. A is in front of parentheses, and B is inside the parentheses. Sometimes the parentheses won't be there, and you'll just have a single number. But what I need you to know is that the B has an exponent of x. Because if I use the power rule, I'd multiply this inside, and B would have a power of x. The B value always has the power of x. A does not. The A value is my initial amount or initial value. Can you guys think back to linear equations? The thing that was the initial value was where on my graph?
The y-intercept.
The y-intercept. Same thing happens here. So your A value is your y-intercept. Since it's still my initial value, that idea has not changed. But the letter changed. The B, the y-intercept. The B here, when the thing that's in parentheses, is called the rate or the factor. Okay? It's not a rate of change this time because that's a slope. We're not changing by the same rate every time. We're changing by a ratio. So the factor that it's going to be changing is that B. In my penny example, what did I begin with?
1.
A penny.
1 penny. So my A value would have been 0.01 because I started with a penny. And what did it do every day?
It doubled.
It doubled.
What number you think is going to show me double?
2.
2 to the x. That's the formula that the guy used to tell you how much money you would have made from McDonald's. He took a penny and he doubled it every day. That's the rate or the factor that I'm using. Okay? So, those are the parts you need to know. You need to know that the A is the initial value or the y-intercept, and that the B, the number in parentheses or the number with the exponent, is the rate or factor. For those of you who can't see what I wrote up here, this was the penny example. Y equals 0.01 times 2 to the x. My bad, I wrote it kind of small. That was the penny example. It started with began with the penny and it doubled every time. Now, how to decide if functions are linear or exponential? Math-wise, you need to look at the inputs and outputs. If the outputs of a table are not being added something every time, but instead are being multiplied by a constant factor or base or rate, multiplied, not added, and linear we added every time, right? For multiplying, that makes it exponential. And these y values form a constant ratio. But what we're actually going to do to decide if these functions are linear or exponential is we're going to graph them. And by we, I mean Desmos is going to graph them. Yeah. Because we need to see if they make lines or curves. That's going to help me know if it's linear or exponential. So the first thing I want you to do is go to Desmos and add a table. So press the plus sign and then table. And I want you to type in this linear table. I know it's going to be linear, but I want you to see what happens when you type in the table. I'll give you a couple seconds to do that. So what does this look like now that you've graphed it? A linear. It looks like a straight line, right? All of those dots, if I were to connect them, it formed a straight line. Since they're in a straight line, that makes this linear. This is going up by 2 every time because I'm adding 2. That makes it linear. That's my rate of change. But if I put in the exponential table, so delete that one out, and I want you to type in the exponential table, it's going to look different. And I want you to see how it looks. You might have to zoom out on this one, by the way. So add table. Type that in and let's see what it looks like. What do these dots actually look like now? A curve. It kind of looks something like this, right? And then this one was like way up there. If I were to connect the dots with that, that is a curve. Exponential functions are no longer lines, they're curves. Instead of adding every time, do y'all notice that to go from 4 to 8 to 16 to 32, I'm going to be multiplying by 2 every time? Times 2, times 2, times 2. That's my constant ratio. Because I'm multiplying by the same number every time, that's my constant ratio. And that's why this changes in a curve pattern instead of a line. Lines happen when we add, curves happen when we multiply. So we're going to split the next 4 problems up. If you're sitting in a desk labeled number 1, you've got problem number 1. If you've 2 got 2, 3 has 3, 4 has 4. You only have 1 problem to do, and then we'll trade answers with each other so we all have it. But I'm going to give you about 30, I'll give you a minute because it's typing, a minute to do your problem, and then we'll come together and talk about it. We should have shared, person number 1 should have said that theirs is an exponential. Yep. And if they drew a sketch, it looked something like this. If you did not draw a sketch, go ahead and draw a sketch now. It was a curve. The second person should have shared that theirs was linear. I did that curve. Theirs was a straight line, kind of something like that. The third person should have shared that theirs was also linear, because theirs made a straight line, but it went down. And the last person should have shared that theirs, even though it has decimals, was very easily seen to be an exponential. It curved up, because the numbers were increasing. Did every group do a good job? But we learned now, right? Let's give each other another fabuloso just because we're feeling it. Fabuloso. Yes, love it. All right. The next concept we need to be able to do with exponential functions is called evaluating. Take your highlighter and highlight the word evaluate. We've talked about this word before, but it's been a minute. Does anybody remember what evaluating a function means?
Look at it. Look at it.
So it starts with the thing you need to do starts with a P. It ends with plug in.
Plug in.
We're going to plug in a number, okay? So evaluate means to plug in. So if you notice what they gave me. They gave me.
Shut up, man.
Be nice. Nice, please. They gave me an exponential equation. Y equals 3 to the x power. The x is an exponent. Cool. And then they said x equals 5. What am I doing with this information?
You're plugging it in.
I'm plugging it in. So in my brain or in my calculator, I want to figure out what 3 to the 5th power is. Don't say 15. What is 3 to the 5th power?
15.
Yikes.
243.
243. How did you do that?
Who said that?
She put it in her calculator. That's fine.
You cheated.
So 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. 81 times 3 is 243. So let's say you go home and you need to calculate or evaluate some of these functions, but you don't have a graphing calculator with you. Oh, wait, you do. You do because you have Desmos. Let me show you how to do this on Desmos. So let's try this number 6. We have y equals 1/4 to the x power. What number am I plugging in there?
3.
3. So I'm gonna do 1/4 raised to the 3rd power. Are the parentheses important?
Yes.
Okay, either with your calculator or with Desmos, I would like for you to calculate or evaluate
Please don't say it out loud.
1/4 to the 3rd power. Don't say 1/12. So with your brain or your calculator, you got 1/64. Don't forget that trick with Desmos to change it back to a fraction. It's the little symbol that shows up like this. That means fraction in Desmos, okay? One last one. We've got y equals 3 times 4 raised to the x power. What am I plugging in this time?
3 parentheses 4.
I'm plugging in 4, yeah. Okay, you tell me the whole thing. Okay, I have to type that whole thing into my calculator or into my Desmos. You don't need the y equals, but you need the numbers. So in your Desmos or in your calculator, can you evaluate this function for me?
What was the second answer?
You had it. What do you mean?
It's on the board.
When you evaluate this, what do you get?
768.
Very cool, 768. That's evaluating. It's real easy. Brain or calculator or your Desmos, which is technically your calculator. Let's go to the inside of this packet. There's a lot on here, but that's okay. I got you. She lied. Okay. Right now I can tell you we are not going to talk about number 10 because number 10 I'm actually going to tell you how to do on that second piece of paper you picked up. So if you want to mark it out so you're not even worried about it, go ahead and mark it out.
Number 10.
We're going to do the skills from number 10 on the other sheet of paper, so I'm just not going to worry about number 10. Wow, y'all are really marking it out today. So what does an exponential graph look like? If you would please remember, because we don't have this on a formula chart, so we're going to write it down 1,000,000 times before we have it memorized. An exponential graph is y equals a parentheses b close parentheses raised to the x power. Write that down for yourself on there so you have it right in front of you. There are 4 options for what kind of graph you might have here. 2 of them are more popular than the other 2. These first 2 right here, where a is positive, are the ones you're going to see most often because they actually happen in real life. The other 2 are a possibility, so we're still going to talk about them, but they won't happen as often in real life. So we're not as worried about those 2. But what we need to know is if the a is positive. What was the a value? What did it stand for? A chorus of us.
Initial value.
The initial value or the
Y-intercept.
y-intercept. So if the a number is positive, my y-intercept is going to be a positive number. My whole graph is going to appear in the top 2 quadrants, which is quadrant 1 and quadrant 2.
1 and 2.
If my a value is negative, my entire graph is going to show up in the bottom 2, in 3 and 4. But like I said, the a is positive is way more typical of what's going to happen in real life. But it totally could happen that you have an a is negative. The other thing we're going to look at is your b value. So the number in that parentheses. If your b value is bigger than 1, which means it's like 1.5, 2, 100, 10, big numbers like that, you're going to have what's called a growth graph, okay? It's increasing. You see how it's going up? It's increasing. This is like the penny example because it doubled every time. That was a 2, so it got bigger. If, though, that b value is a fraction between 0 and 1, so it's never going to be negative. So basically, it's a fraction like 0.2 or 1/2 or 0.75 or 7/8, a fourth. It's going to be decaying is the word we're going to use, but yeah, it's going down.
That's a big word.
Decay?
Not really.
It's 5 letters. You're right. When animals die, they decay, and this is how they decay. I'm going to teach you about it. For real.
No.
No, not today. That's next class, so y'all get all weekend to look forward to that.
Is it gonna be like the animals going on the escalator and then coming out as food?
Oh, the function notation? No, it's grosser than that.
Oh my God.
Just you wait.
Yes!
Okay. Wait, bring it back.
You shouldn't have seen it. It was so fun.
That's disgusting.
No, I leave that for your science.
Well, I'm gonna have
That was hilarious.
So,
to
you have to leave, you have to leave. All right, focus up here. We talked about the two most important ones. We've got a growth and decay. For me, I'm going to be most worried about you being able to identify my initial value on a graph showing me where A should begin and whether it should be going up or going down. I'm not going to require you to detail graph for me just yet, because Desmos can do that, so we don't need to practice what a computer can do for us. We're going to practice making ideas in our head make sense on paper. It starts here, it should go up. It starts here, it should go down. That's what I need you to be able to do. Think you can handle it? Cool. Here's the vocabulary we're going to talk about today. Some of it we've already talked about ourselves. We talked about the initial amount. What letter was my initial amount? A. It was 2 on those graphs, you're not wrong. But the letter representing it is the A. And this is also my y-intercept. In word problems, you're looking for words that talk about the beginning. So starting value, initial amount, beginning amount, I don't know. Words that mean you're starting with this, that's going to be the number you use for the initial amount. Like our penny, we started with a penny. The constant ratio is that B. This tells me how we change. Okay, it's going to tell me whether I'm increasing or decreasing, whether I'm growing or decaying. Remember again, if that number is bigger than 1, we're growing. If the number is less than 1, we're decaying. Now this next word, I'm going to let you get the giggles out, and you have to try say it at least 4 times because you're going to say it wrong the first 2. It's fine. This next word is called a horizontal asymptote. Say it a couple more times to yourself. The more you say it, the easier it will get. Asymptote. This is legit a math term that you're going to need to know. Which direction is horizontal? Is horizontal up or down or side to side? Side to side. Cool. So we're talking about a horizontal asymptote. Here's what an asymptote is. Do any of y'all have annoying little or older brothers?
Yes, I have annoying
Because
little brothers.
I do. I had an annoying older brother.
I have 3 annoying little brothers.
Wow, you win the lottery. Okay, so here's what my older brother used to do when we were kids. My brother used to, on road trips especially, when you can't leave because you're in a car, he'd sit there next to me and go, I'm not touching you. I'm not touching you. I'm not touching you. You know that game? I feel you. No lie. Okay, no lie. One time, we were on a car trip. We had just left my grandma's house. She lives in Balmorhea, so it's 9 hours away in a car. Okay, we're driving. We're maybe 45 minutes into the drive, and I'm looking out the window at like the oil derricks going, and my brother doesn't put his finger right here and say, I'm not touching you, puts his fist. And then he called my name and said, hey, Kathy, and I turned so fast, he almost broke my nose. That was a fun 9-hour car drive, let me tell you. Woo! Anyway, sorry.
Miss, you know you didn't put the hammers down.
No, all I did, honestly, I cried because my nose, when you hit your nose, your eyes literally cry. And he got in so much trouble. I got to pick every movie and every song we listened to for the 9 hours we drove home. Woo! All right, so. He almost broke my nose. So a horizontal. Bring it back. A horizontal asymptote is kind of like the annoying little brother, or older brother in my case, that's saying I'm not touching you, because it is defined as an invisible, which is why I dashed it, invisible line that a graph approaches. sort of. A graph approaches but never touches. I will move. I'm standing right in front of it. Okay. An invisible line that a graph approaches but never touches. An invisible line that a graph touches or approaches but never touches. Okay, so this is the I'm not touching you line. It's invisible because it's not actually graphed. You just know that it exists because there are boundaries to exponential functions that it will never touch. That is called the horizontal asymptote. For every exponential function that we're going to talk about in this class, because there are times it's not true in maybe pre-cal or calculus, the horizontal asymptote is the x-axis, or the equation y equals 0. That's the sort of thing that you just have to memorize because it will never be a different answer for me. The invisible line that the graph approaches but never touches is y equals 0. A Hoy line at 0. Horizontal at 0, which is also the x-axis. But let me prove this to you because you won't believe me unless you see it. Is always going to be here, okay? This, for my class, does not change. The horizontal asymptote for all of the graphs at the top of our paper is the same. If I drew in the horizontal asymptote here, that graph is never going to cross that green line. This one, it's never going to cross the green line. It's going to get real close, but it will never touch it. This one, it will never touch it. This one, it will never touch it. It'll get real close, but you have to zoom like I did on there, but it will never touch it. That y equals 0 is always the asymptote for me. That's something you can just memorize. The last thing we're talking about today in regards to exponential equations is their domain and range. Now, domain and range has not changed. What is the domain?
Dr. XY.
Dr. XY lets me know that the domain is which letter?
The X.
And the range is which letter? Y. Okay. Then Delore the robot helps me remember that I'm describing this graph from the left to the right, and for the range from the bottom to the top. Now here's the nice thing about domain and range with exponential functions. Unless I give you like one of the puppy dog ones where it's going to have endpoints that you can see, like you know what I'm talking about when I say the puppy dogs? When we had to do the domain and range of the puppies, and you could see the beginning and end. That's like different. Follow the rules for linear there. But if I give you domain and range, there's only a couple options you can choose. If I give you a straight up math question, where I give you an equation, I don't tell you it represents time, I don't tell you it represents money, your domain is always, what is that symbol? What is that symbol?
Numbers.
All real numbers.
I knew that.
All real numbers.
No, that's the you're thinking this one. That's the paragraph symbol. You're not wrong though, it's super close. Okay, that is all real numbers. All real numbers. You can write the words out or you can write the fun and funky R. But if I give you just a regular equation to ask you for the domain, boom, you know it's all real numbers. If I gave you a real world question where I'm telling you this is bacteria growing.
All numbers.
Oh, it's not all real numbers.
Fake numbers.
All positive numbers.
Yeah, that's what I was gonna say next, man.
Which is written as x greater than or equal to 0. Those are all my positive numbers because if I'm telling you this is how bacteria grows over time. Can I have negative time? No.
Yes,
So it has to start at 0 and go on. You can't have negative time travel. That doesn't happen. We can wish it does, but it doesn't.
Theoretically, it is possible. Theoretically.
I don't believe so.
Theoretically.
I don't believe so.
You can't go back in time. Yes, you can. You can go forward.
Time is a social construct, so I don't believe you can go back in time because we have defined time as always going forward. So I don't believe so. Whatever. I digress.
How can it reverse?
Hold on. This is not a time travel conversation. I need you to know that if we give you a real world scenario, if I tell you this is buying a car, if I tell you this is buying a house, if I tell you this is anything that has to do with real life, you can't time travel, so your domain is just positive numbers. There are only 2 options for range in this class. If your graph appears in quadrants 1 or 2, which means it's at the top of, okay, if your graphs show up here, your range is y greater than 0. If your graphs show up below in the bottom two quadrants, what do you think that range is going to change to? Less than 0. Because the whole graphs, either if it's growing or decaying, appears above that line 0, because it can't touch it, so it's never going to go below it, because it can't even touch it. Or it's going to be all below it and get close to it, but never touch it, because it literally can't touch it. It's an asymptote. Now question, why am I not putting the or equal to here?
Because
This is a thinking
it
question.
can't go less than 0. Right?
It can't go less than. Can it be equal to 0?
Yes.
I thought you told me it couldn't touch it.
It can't. Oh wait, no.
It can't because 0 is the, what's that word?
Horizontal.
Yeah, horizontal asymptote. So I'm not allowed to even touch 0, which means it can't be equal to 0. So I don't put that or equal to underneath it. Okay, it's always just greater or less than. If it's above, it's greater. If it's below, it's less than. Okay. All right. We move over to the actual questions here. I'm going to give you something like this. And I'm going to ask you to graph the function. But on your homework, I use the word sketch. So we're going to change the word graph to sketch. Because sketching means I don't need you to be accurate. I need you to give me a sketch. Okay, sketch the graph. I'll teach you how to sketch things. It says identify and describe the initial amount, constant ratio, asymptotes, domain, and range. Now, your function should be y equal to a times b to the x. F of x and y mean the same thing, so whatever. But what is my initial amount in number 1?
Wait, can you repeat the question?
What is my initial amount?
It's
It's 8 because the a and the 8 are in the same spot. Cool. The initial amount is 8, which means that's also where my graph crosses the y-axis.
And 1/2 is the
Y equals a times b to the x is what I wrote up there. It's the formula. Which means what number is my constant ratio?
1/2.
1/2. Which means, is this graph going to be increasing or decreasing?
And decreasing.
Decreasing because it's less than 1. I don't need you to be accurate. Desmos can take care of that. If I wanted accuracy, I'd look there. I just need to know if you know it's going up or going down. Doesn't have to be pretty. I can make this pretty. But I need you to know it's going down. Because it's a half. Halves are less than 1, so this is going to decrease. Now, what is the answer you should give me every time you talk about the asymptote?
0.
What equals 0?
Y.
Y equals 0. You could also write the x-axis. That's fine. Go ahead and draw it in for yourself, too. This is the dashed line. If you want to use your highlighter, that's fine. The dashed line that the graph will get close to but never touch. I'm not touching you line.
Bro, I hate that.
Did any of you guys, did I give any of you context on what this is describing? No, so what is the domain without context?
No, 0.
What?
No, I don't know.
Does it stop on the left?
No, oh.
Does it stop on the right?
Infinite.
It goes to infinity both sides, so how do we write that?
The R weird thing.
The R weird thing. All real numbers. All real numbers. If you want to write out the words so you know what that symbol means, that's fine, but that symbol means all real numbers. Now, does this graph appear above or below your asymptote?
Above.
So I'm going to use y above 0 because it's all above the 0 asymptote.
It's hard.
It's new.
I don't like it.
That's why it should be a little hard because it's a new concept.
I don't like
It will get easier as you get more comfortable.
it.
Okay, I'm still going to do number 9 with you because I don't feel like we're ready to try one on our own. Is that fine?
Yeah.
Yeah.
Before I do that, do I have any questions on number 8? Yes, what is it?
Wait.
Just stop playing like that.
All right, let's look at number 9. If we write our formula above it, which I want you to do, y equals a times b to the x. What's your a value?
0.
Ooh,
Wait, X. Nothing.
2.
If nothing,
Ain't that 2?
1.
It's 1 then. It's 1.
Invisible one.
it's an invisible 1 because the 2 is in parentheses and has an exponent of x. So that's not my initial value. My initial value is actually a 1 right there.
Okay.
Very good.
How we know the number is our initial value? Right.
A is always your initial value.
But how we know which one is A?
It does not have an exponent of x. Yeah. So that means we're also going to begin our graph at 1. 2 is called my what? B value, which is the constant ratio. Tight. All right. So is this graph going to be going up or going down?
Going up.
Up, because 2 is a big number. It's going to be doubling. So this will be a sketch that looks like this. Ooh, that's not cute. Let me do that again. That one's better. Well, I kind of missed my y-intercept, but you get it. My bad. It's going up. If I wanted to be accurate, I could. I could use Desmos to get points, plot them, and play connect the dots, but like,
No, thank you.
we're sketching because it's new. What is the asymptote for number 9?
0.
What equals 0?
Y.
Thank you. That's a line, so I need an equation for it. Y equals 0 is still my asymptote. It will never touch that line. It'll get real close. But if you zoom in, it will never touch.
Like super, really.
Yeah, I had to zoom in a lot on that example I showed y'all earlier. What is the domain of this function? It extends all the way to the left and the right with no context, so it's all real numbers. Is this graph showing up all above the asymptote or below the asymptote?
Above.
So this is y greater than 0. Very cool. Major questions before we move on from this section?
Can I have $5?
Was that thunder?
Nah, man. I think it's somebody knocking. This says how to use Desmos to find an exponential regression. I need you to highlight 2 things on this page if you have a highlighter. Exponential regression and Desmos. There are different rules entirely. If you wanted to do this on the calculator, I can print them out for you and it would be the same thing but different buttons. I believe the calculator is more confusing and less intuitive. Plus Desmos is free. So we're going to learn how to do this on Desmos so you can actually do your homework at home, since majority of you don't have a graphing calculator at your house, which is totally cool because now you have Desmos, which is a graphing calculator. So step 1 says to add a table. Go ahead and add a table into your Desmos. Clear everything out and add a table. This is going to sound familiar because we've actually done this for linear, but it's kind of cooler for exponential and way less confusing. And you're going to fill in that table, making sure it says x1, y1 at the top with the time versus temperature graph that we have on here. Yeah, that up there. Yes. You're filling in Desmos x1, y1 with the time versus temperature graph. Now y'all are doing this. I'm not going to show you because you can follow along as I do this.
Wait. Oh, that's no B.
The zoom fit on this particular problem looks real funky, so just trust that it's exponential. It does kind of look like they're in a... Say what? It is going to be on your homework. Some like this. Okay?
On the very last questions.
Oh my god.
Now, after you type in the table, you should press zoom fit, which is the button that looks like this. It makes a really weird choice for this particular problem. It kind of looks like they're linear. But they're truly exponential, and I promise, and it will make sense when we type in the next part. Then I need you to type in the fun and funky version of y equals ab to the x, where x1 and y1 are there instead of just regular x and y, and instead of an equal sign, I have that squiggly line. Y'all remember using this before?
Yeah, you do central.
And then
Control.
It is, yeah.
It should be shift, I believe.
Oh, yeah.
Okay, and then to make this an exponent, what was that shortcut we used? Or it's shift
Shift 6.
6 to make an exponent. Shift
Look at that.
6. Okay, so it should be with both the table and the fun and funky equation. The moment you finish typing the fun and funky equation, a bunch of stuff happens. Bloop! And you should have an A and a B that has shown up on your screen. I'll give you a second to catch up. When you've done this, Desmos sets up some parameters for you, and it gives you an A and a B. All you have to do is take those A and the B's and put them in an equation. I didn't tell you how to round, so I don't really care how you round. But to answer this, to write an equation for this table, all we would do is say y equal to 174.8, open parentheses, 0.89. Is that what the number is?
Yeah, 0.897934.
Okay, we'll do 0.989 or 898 raised to the x power. That is the equation that makes this table. You didn't have to calculate things that are kind of complicated to calculate if you do it by hand. Desmos will help you write an equation. Anytime you see a table or a graph with coordinate points that wants you to write an equation, you just need to know what type of equation it is. If it says linear, you use the linear equation, which is up here on the back wall. If it says exponential, use the exponential equation that I just taught you, that is also going to be on a poster that I will shortly hang on the back wall. You just have to remember how to change the annotations. X's and Y's get a 1 next to them, and the equal sign turns into like a squiggly. Okay? This will eventually be up on the wall. I just haven't hung it up yet. So here's what we're going to do to practice this. You're going to delete everything out of your computer, and if you're sitting in a desk labeled A, you're going to do the days versus views graph. If you're sitting in a desk labeled B, you're going to do decade and population. Nobody's doing this one. Not log out of everything. Delete the table and the equation that you just did and retry it. Okay, I'll give you some time to work on this and we'll talk about it. That we have time to keep going. So here we go. Person A, you should have put in your graph in your table and done the regression line to get that y should have been equal to, and I might have rounded differently than you, so give yourself grace on the rounding. 9.5, open parentheses, 7.4, close parentheses, raised to the x. How'd we do?
That's what I got.
Woo-hoo!
I put 52, so.
That's what I'm saying. The rounding could be different.
I put 9.52.
That's fine. If you were B, you should have gotten y equal to 14.56 times 1.70 to the x, or something similar. Maybe I rounded differently than you because I didn't tell you how to round. That's what I'm talking about. We can do it. Anytime you're given a graph with coordinates or a table and you're asked to write the equation, you need to think about this. Writing an equation in Desmos is a good way to write an equation. Okay? Are there any last minute questions before we go to a GimKit? Yes questions or yes GimKit? What's up? Yes, you have to play GimKit.